This text describes the import of libraries required for various data tasks. 1. Numpy, imported as NP, used for efficient numerical operations with arrays and matrices. 2. Pandas, imported as PD, used for data manipulation with structures like dataframes. 3. Matplotlib, pyplot, imported as PLT, a plotting library providing a MATLAB-like interface for visualizations. 4. I/O, allows working with streams for input-output operations. These libraries enable reading, manipulation, numerical operations, visualization, and input-output tasks in fields like data analysis, machine learning, and scientific computing. This method allows users to upload files to a Google Colab notebook. It utilizes the Files upload function provided by Google Colab for uploading files. Users are prompted to select a file from their local machine, and the chosen file is then uploaded to the current working directory in the Colab environment. After the file is uploaded, the code goes through the uploaded files, displaying the file names and their respective file sizes in bytes. This approach proves beneficial when needing to handle files in a Google Colab notebook, like analyzing data from external sources or saving computation outcomes. It grants an efficient means to move files between a local machine and the Colab environment for further processing and examination. This script reads a CSV file named crude-oil.csv and imports its contents into a pandas DataFrame object named df. The pandas read_CSV function is utilized to read the CSV file and present the data in a structured tabular format for convenient data handling and analysis. This script enables us to interact with and manipulate the data stored in the crude-oil.csv file by leveraging the advanced functionalities offered by the pandas library and Python. By loading the data into a DataFrame, we can execute diverse data manipulation tasks, analyze the dataset, create visualizations, and extract valuable insights to support decision-making or additional data processing. The df head function in Python's pandas library is often employed for data analysis to quickly examine the initial rows of a data frame. By default, it shows the first 5 rows, but you can specify the number of rows to display by providing a number as an argument inside the parentheses. This function aids in obtaining a quick summary of the dataset, comprehending its arrangement, column names, and the data types included. This script displays the dimensions of the dataframe, df. The shape attribute of a dataframe provides information about the number of rows and columns in the dataframe. For instance, if df contains 10 rows and 5 columns, the output will be 10, 5. Utilizing this script allows us to efficiently grasp the size of the dataframe, aiding in tasks such as data manipulation, analysis, and debugging in data science and data analysis projects. This method checks for missing values in a dataframe. Using the isNull method, it creates a new dataframe with Boolean values identifying missing values. Sum is then used to count true values in each column, indicating the number of missing values in the dataframe. Detecting missing values is crucial for data preprocessing and analysis as they can affect the reliability of the results. This code helps quickly identify columns with missing values and determine how to manage them, such as imputing them, deleting rows with missing values, or applying other data cleaning techniques to enhance data quality before analysis. This script fills missing values, NaN values, in a dataframe with the last known value in each column using the forward fill method. The forward fill method replaces each missing value with the last non-missing value that occurs before it in the column. The purpose of this script is to manage missing data in financial data within a dataframe. In financial data analysis, missing values can create issues, so replacing them with the last known value is a standard approach to maintain data continuity. By employing forward fill, the script ensures that the most recent information is used to substitute the missing data points. In conclusion, this script guarantees that the financial data remains coherent and uninterrupted by filling missing values with the latest available values. This text describes how to create a plot showing the relationship between the close price of a stock, or any financial asset, and the corresponding dates using the matplotlib library. 1. A subplot is created with a single plot, one row, one column, and a figure size of 10 by 10 using the subplots function. 2. Two variables, close_price and date, are extracted from a DataFrame, df, where date presumably holds the dates corresponding to the close prices. 3. The subplot at position 2, 1 is selected for customization, turning on the grid with plt grid true. 4. The X label, Y label, and title for the plot are set to time, close price, and price versus time, respectively. 5. The close price data is plotted against its index, using a green line to visualize how the close prices change over time, aiding in observing trends and patterns. This code is crucial for visualizing financial data, especially stock prices, to help analysts and traders gain insights into historical price movements and make informed decisions based on trends and patterns in the data. Visualization assists in recognizing patterns, identifying support and resistance levels, and forming trading strategies. This process prepares the close values of a DataFrame column for further analysis or modeling. What it does: 1. Extracts and converts the close values into a numpy array. 2. Converts the values to the float 32 data type. 3. Reshapes the array using reshape -1, 1 to create a 2D array with one column and an appropriate number of rows. 4. Stores the processed values in a variable called closing_stock. This snippet ensures that the close values are formatted correctly for tasks like machine learning, statistical analysis, or visualization. By changing the data type and reshaping the array, the efficiency and accuracy of subsequent analytical processes are enhanced. This snippet accesses all the elements in the first column of a numpy array called closing_stock. The syntax 0 is utilized to select all rows in the first column, index 0, from the numpy array. This method is beneficial for extracting specific columns or rows from a multi-dimensional numpy array. In this scenario, the code is likely used to extract values from the first column of the closing_stock array for further processing or analysis. By employing this method, we can conveniently handle specific data within the array without the manual iteration of each element. This streamlines data manipulation and analysis tasks, enhancing the code's conciseness and efficiency. This snippet works with a variable named closing_stock, assumed to be a numpy array with multiple rows and at least one column. It first extracts values from the first column of the closing_stock array and assigns them to a new variable called stocks. Then, it reshapes the stocks array to have the same number of rows but only one column by using the dimensions len stocks 1. This process is beneficial for adjusting the shape of data within a numpy array. Reshaping might be necessary to perform certain operations, calculations, or to match the expected input shape in some functions or machine learning models. Reshaping is crucial for tasks like model training, data processing, and visualization to ensure that the data is in the correct format and dimensionality for further analysis. The min-max scalar from the scikit-learn library in Python is utilized for data preprocessing, ensuring each feature is scaled and translated independently to a specified range, typically between 0 and 1. Feature scaling is essential in various machine learning algorithms as it normalizes the range of independent variables or features, improving model performance and efficiency. In this demonstration, the variable stocks data is transformed using min-max scalar. The fit_transform method fits the scalar to the data and adjusts it to values within the desired range. Min-max scalar ensures all features are on a consistent scale, preventing any single feature from dominating the learning algorithm due to its magnitude. This practice optimizes data preprocessing for machine learning models, resulting in enhanced performance and accurate predictions. This process divides a dataset into a training set and a test set based on a predetermined percentage split. 1. The total number of items in the dataset is determined using len stocks. 2. 80% of the dataset length is calculated using int len stocks *0.80 to set the index where the training set ends. 3. The remaining 20% of the dataset length is calculated as len stocks train to define the size of the test set. This step is crucial for training machine learning models as it enables the evaluation of a model's performance on new data. By splitting the dataset, the model can be trained on one portion and tested on another, aiding in assessing the model's ability to generalize and identifying potential overfitting issues. Printing train and test data is a common practice in machine learning and data analysis projects. It helps in displaying the content of these variables, typically used for training and testing machine learning models. This action facilitates data exploration, enabling quick inspection, verification of data shape, contents, and preprocessing requirements. Moreover, printing these variables aids in debugging to ensure correct data usage and assists in verifying the accuracy of data loading and splitting processes. Ultimately, this practice helps maintain data integrity and prevents errors that may occur due to improper data manipulation. In essence, printing train and test data is a useful method for inspecting, verifying, and debugging data in machine learning and data analysis projects. This process selects a segment of a list named stocks and assigns it to a new variable named train. Here's how it operates. Slicing is used to choose a segment of the list stocks. The slice 0 train specifies that it should begin from index 0 and extend up to, but not including, the index indicated by the value of the variable train. The selected segment of the list is then assigned to the variable train. This method is valuable for creating subsets of a list for specific purposes, like segregating training data from testing data or executing operations on a subset of the data. By utilizing this approach, you can easily access and edit pertinent segments of a list without altering the original list. This operation involves extracting a section of a list called stocks. It retrieves all elements in the stocks list starting from the index position len train until the end of the list, then saves them into a new list named test. This procedure is commonly used to divide a list into separate segments, often for training and testing machine learning algorithms. The train list usually holds data intended for training the model, while the test list holds data for testing the model. This partitioning of data is essential for precisely assessing the model's performance and preventing overfitting. The train and test arrays are being transformed into a two-dimensional array with one column by the provided code snippet. The number of rows in the reshaped arrays is specified using the len train and len test functions. This type of transformation is commonly necessary when working with machine learning libraries such as scikit-learn or TensorFlow, as many machine learning algorithms require input data to be in a specific format, usually a two-dimensional array. By reshaping the arrays in this way, the data is properly formatted for machine learning algorithm processing. This enables the training of models and the generation of predictions on the data. To obtain the dimensions, number of rows and columns, of two datasets, train, and test, we can use the shape attribute of a DataFrame in Python. The first value in the shape attribute indicates the number of rows, while the second value represents the number of columns. Printing the shape of both the training and testing datasets allows us to quickly confirm the data size, aiding in understanding the data structure and conducting initial data exploration. This step helps ensure data has been loaded accurately and provides insight into the number of data points in each dataset before proceeding with any analysis or machine learning tasks. The function named process_data takes two arguments, data and n_features. This function processes the data by dividing it into two arrays, data X and data Y. Data X represents a set of input sequences, with each sequence composed of n_features elements. Data Y consists of output sequences that correspond to each input sequence in data X. The function traverses through the data array, capturing a sequence of n_features elements as input, data X, and the subsequent element as output, data Y. This process is repeated for all feasible sequences within the data. This function is convenient for data preprocessing and structuring sequential data for machine learning models, particularly for tasks like time series prediction or sequence prediction, where historical data serves as input for anticipating future data points. In summary, this function aids in converting raw data into a suitable format for modeling using machine learning algorithms. This procedure is responsible for preparing the data for training a machine learning model. Here is how it operates. 1. n_features equals 2. Determines the number of features to be utilized for training the model. 2. trainX, trainee equals process_data, train, n_features, invokes the process_data function with the training data, tran and the specified number of features and _features. This function is likely to preprocess the training data by extracting features and labels, and then returns two arrays, trainX for the features and trainee for the corresponding labels. 3. testX, testY equals process_data, test, n_features. Similarly to the previous step, this line processes the test data, test, using the same process_data function to extract features and labels, and then separates the processed test data into testX and testY. Utilizing this process is crucial in the machine learning workflow as it readies the data in a suitable format for training and testing machine learning models. By preprocessing the data before inputting it into a model, we boost the model's performance and accuracy. This approach also contributes to maintaining consistency and efficiency in data handling, which is essential for the model's success. This text discusses the importance of understanding the shapes of four arrays: trainX, trainee, testX, and testY. These arrays are likely used for training and testing a machine learning model. Examining the shapes of these arrays helps us determine the number of data points and features in each array. This knowledge is valuable for debugging and ensuring that the data is properly loaded before training the model. Understanding the dimensions of the data is essential in the machine learning process. Being aware of the shapes of these arrays is vital for a successful machine learning workflow as it guarantees that the data is appropriate for the tasks at hand and that the model can be trained effectively. This process reshapes the two-dimensional arrays trainX and testX into three-dimensional arrays. An additional dimension is added at index 1 during the reshaping to align with the original array's shapes. The main purpose of reshaping the arrays in this manner is to conform to the input shape required by various machine learning algorithms, particularly neural networks. Typically, deep learning frameworks expect 3D data input with multiple samples, time steps, and features. By reshaping the arrays like this, we are adapting the data for training and testing in these algorithms. This text explains the purpose of various libraries commonly used in machine learning applications. 1. Math**. This library offers mathematical functions and constants, serving as a standard Python library. 2. Keras. Models. Sequential**. Sequential and keras allows for building models layer by layer, commonly used in constructing neural networks. 3. Keras. Layers. Dense, batch normalization, dropout, activation, LSTM, GRU**. These represent different layers used in Keras neural network models. Dense is a standard fully connected layer. Batch normalization normalizes input layers. Dropout prevents overfitting. Activation specifies the activation function. LSTM and GRU are recurrent neural network layers. 4. Keras. Optimizers. Atom, SGD, RMS prop ***. These optimization algorithms minimize loss functions when compiling a Keras neural network model, aiding in training. 5. Escalern. Preprocessing. Min-max scalar ***. Used to scale numerical data to a specific range. This preprocesses data before input to machine learning models. 6. Escalern. Metrics. Mean_squared_error***. This function evaluates regression model performance by calculating mean squared error between actual and predicted values. These imports are crucial for constructing and training neural network models, as well as conducting data preprocessing and evaluation in machine learning projects. 2 callbacks commonly used for a neural network model in Keras are: 1. Reduce LR on plateau. This callback decreases the learning rate if a metric stops improving. Specifically, it reduces the learning rate by a factor of 0.1 if the validation loss does not improve by at least 0.0001 for one epoch. This dynamic adjustment of the learning rate helps the model converge more accurately during training. 2. Model checkpoint. This callback saves the model weights during training. It monitors the validation loss, saving the weights to the specified file path whenever the validation loss improves, in this case, maximizing it, as mode equals, max, is set. By setting save_best_only equals true, only the weights corresponding to the best validation loss are saved. Using these callbacks in training enhances the efficiency and effectiveness of training neural network models by adjusting the learning rate and saving the best model weights for future use or further training. This text describes the architecture of a neural network built using the Keras framework with TensorFlow backend for training deep learning models. Here is an overview of the steps followed in the code. 1. A sequential model is initialized to add layers sequentially. 2. A GRU layer with 512 units is included as the first layer with an input shape of 1 n_features to handle input sequences of shape 1 n_features. The return_sequences parameter is set to true to return the full sequence of outputs. 3. A dropout layer with a rate of 0.4 is added after the GRU layer to prevent overfitting by randomly setting input units to 0 during training. 4. An LSTM layer with 512 units is added, which can learn long-term dependencies. 5. Another dropout layer with a rate of 0.4 is added after the LSTM layer. 6. A dense layer with 128 units and ReLU activation function is added for nonlinear transformations. 7. A dense layer with 1 unit and no activation function is added as the output layer for regression tasks. The model summary function displays a summary of the model, showcasing the layers, output shapes, and number of parameters in each layer. It helps in debugging and verifying the model architecture. In conclusion, this code constructs a deep learning model with GRU and LSTM layers for processing sequential data. Dropout layers aid in regularization, while dense layers introduce nonlinear transformations. The model is suited for regression tasks, focusing on predicting continuous values. This configuration sets up a neural network model for training with the following settings. 1. Loss function ***. The model will use mean-squared error as the loss function to minimize during training, suitable for regression problems. 2. Optimizer ***. The Atom optimizer with a learning rate of 0.0005 will update the weights of the neural network to minimize the loss function. Atom adjusts the learning rate during training. 3. Metrics ***. Mean-squared error will be used as a metric to evaluate the model's performance during training and testing. Configuring these parameters is crucial for effectively training a neural network model for a specific task. Training a deep learning model involves using the fit function, which trains the model on specified training data, trainX and trainee, for a set number of epochs, 100, with a batch size of 32. Callbacks like checkpoint and LR_reduce are utilized to save model weights and adjust the learning rate as needed during training. The validation_data parameter enables evaluation of the model's performance on a separate validation dataset, testX and testY, to monitor performance on unseen data and avoid overfitting. Utilizing this code is crucial for effective deep learning model training as it allows setting important parameters like epochs, batch size, callbacks, and validation data to enhance model accuracy and generalization. This text explains how to plot the mean-squared error, MSE, and loss of a neural network model during the training process. The first plot shows the MSE of the model, a commonly used metric for regression models. The x-axis displays the training epochs, while the y-axis shows the MSE values. This plot helps visualize how well the model fits the training data, train MSE, and generalizes to unseen data, test, validation MSE. The second plot represents the model's loss during training. Loss indicates the error between the model's predictions and actual target values, with lower values indicating better performance. These plots are crucial for monitoring the training process, detecting overfitting, where training loss decreases while validation loss increases, and determining when to stop training to avoid overfitting. In conclusion, these plots offer insights into the neural network model's performance during training, aiding in evaluation and enhancement of performance. The function named model_score evaluates the performance of a machine learning model provided to it. It requires the model, training data, x_train, y_train, and testing data, x_test, y_test, as input. The function utilizes the model's evaluate method to determine the mean-squared error, MSE, for both the training and testing datasets. It then derives the root mean-squared error, RMSE, from the MSE values and displays the results. The purpose of this function is to assess the model's performance on both training and testing datasets. By computing and showing the MSE and RMSE for each, it helps in understanding the model's predictive accuracy, detecting potential overfitting or underfitting problems, and deciding whether further adjustments or optimization are required. This process accomplishes the following tasks. 1. It utilizes a trained machine learning model to make predictions on the test data, testX. 2. Following the prediction step, it applies a scalar, to reverse the transformation of the predictions. This is crucial if the data was pre-processed or scaled before being used in training the model. 3. Finally, the output of the code displays the first 10 elements of the pred array, which now contain the predicted values in their original scale. Implementing this code is essential when making predictions on data that have been pre-processed or scaled before being input into the model. This process ensures that the predictions are in a comprehensible and relevant format relative to the original data. This text describes the following operations. 1. Reshaping the testY array into a column vector with one column and a number of rows equal to the original number of rows in testY. 2. Applying an inverse transformation using a scalar object to revert the testY data back to its original scale. This is often necessary if the testY values were previously modified for model training purposes. 3. Displaying the first 10 elements of the transformed testY data. Reshaping and inverse transformation are commonly used in machine learning, especially in data preprocessing and model evaluation. Reshaping helps prepare the data for processing, and inverse transformation allows for comparing model predictions or evaluating performance on the original data scale. This snippet uses matplotlib to create a line plot comparing actual prices with predicted prices. Here's the functionality. 1. It adjusts the figure size to 25 by 10 inches for a larger, clearer plot. 2. Actual prices from the testY variable are plotted in red, R, with the label, actual price. 3. Predicted prices from the pred variable are plotted in green, G, with the label, predicted price. 4. The x-axis is labeled as time, and the y-axis as price. 5. The plot's title is set to check the accuracy of the model with time. 6. A legend is added to distinguish between actual and predicted prices. 7. Grid lines are enabled on the plot for better readability. 8. The plot is displayed using PLT, show. This code facilitates a visual comparison between actual and predicted prices, aiding in the evaluation of the model's performance and accuracy in predicting prices over time. The visualization helps in assessing the model's effectiveness and pinpointing any discrepancies between actual and predicted prices. To extract a subset of elements from a list named testY, we can use slicing with negative indices in Python. Negative indices start from the last element in the list with -1, then the second last element with -2, and so on. Slicing allows us to access specific portions of the list without altering the original list. This method is beneficial for extracting elements based on their indices, which is useful for tasks involving data processing. Slicing is a technique in Python used to extract a subset of elements from a sequence like a list, tuple, or string. In this case, slicing the variable pred from the element at index -10 to the end of the sequence allows you to retrieve elements starting from the 10th element from the end of the sequence, index -10, until the last element. The slicing notation, 10, specifies that the slicing should start from the element at index -10 and continue until the end of the sequence. This approach is beneficial for extracting a partial sequence or performing operations on a specific portion of a larger dataset. By using this method, you can focus on analyzing or working only with a subsection of the original data rather than the entire dataset. This approach can lead to improved efficiency in terms of memory usage and processing.